So I hope you know what that we had a pretty significant election on Tuesday, and Proposition 30 passed, which means that we probably won't have any tuition increases for the foreseeable future at UC. There was also one other big result from the election. I don't know if you know what else happened. I'm sorry? All right, maybe. You know, the other big result of the election, which many newspapers reported about, is that Nate Silver won. So, so I don't know if you've been following this, but there was, over the last week or two, there was virtually a war between the political pundits and the statisticians, like Nate Silver, and there are a couple of others who had their blogs where they were publishing their predictions about the elections. And basically, almost the entire media were sort of saying, it's too close to call. It's 50-50, it's a toss-up. And all the statisticians were saying, well, it might be close, but it's, it's at least 75-25 in Obama's favor. So that number kept rising over the last week or two, and was at 90% by Monday. Okay, and so there were two different narratives that were on during this period. Okay, and then there were various so there were various people in the media. These were just some of them. Who is the other person on PBS? Who is the person who always who's the New York Times columnist? David Brooks. So it wasn't even people on the extreme right who were. David Brooks also, sort of talked about all this prediction stuff getting into silly land. Statistics was sort of silly land for him. So it was quite remarkable. It wasn't even just the extreme sort of nuts who were saying this. It was also people who were supposed to be pretty moderate who were saying this. Okay, so, and then there were other newspapers that wrote this. So, it was, is it, maybe I should try to resize it or something. Can I? Yeah. Okay, so this was one of those columns which was talking about how Nate Silver had won the election. It was a revenge of the nerds. And the Data Geek bested many of the cool kid pundits and their time-honored tradition of predicting election results based on gut feeling and a few conversations with unnamed poll campaign aides, undecided voters in Ohio diners, right? So they were sort of basically saying the time of the pundits is over. Now, we've got to, it's math that's going to take over from now on. This played out also on the Stephen Colbert report, where Nate Silver was a guest, I think on Sunday or Monday. Okay, and basically, it talks about how Nate Silver was giving Obama a 92% chance of winning, while the media kept still talking about it as a toss-up. Now, technically, 92% is still a toss-up. It's a toss of a certain coin. It's just not a fair coin. So, right, that's it in sort of slightly more magnified. Okay, and if you actually look at the results, this was the prediction on the blog, and that's the actual, and you can see that it sort of more or less corresponds. As it turns out, at this point, actually, as of now, even Florida has been called. So basically, he got all 50 states right. 51. Oh, okay. So he got 51, maybe. We know he at least got 50 right. I don't know whether he got that one right or not. I'm not sure. Okay. So, okay. So what we are going to talk about today is, so what it takes to do this prediction is, it takes a lot of detailed work and so on, because you have to have pretty detailed models. But we'll talk about the basic science behind it. How do you do predictions of elections in the first place? Okay, so what you do is you pick out a random, you sample random people from the population. Okay, so which doesn't mean you pick a point at random and pick a person at, close by there, because the population is extremely non-uniform. So how do you pick a random person in the population is also very unclear, right? So you probably want to sample New York City more often than almost anywhere else, because it's the densest place in the US. But how, so there are ways of picking a random person. But once you do that, if you were to sample such a random person and ask whether they were voting for the Democrats or Republican, that's the same thing as a flip of a bias coin. Okay, so suppose you happen to know that, some percentage, I don't know what it is, I'll just make up a number, suppose you happen to know that, 48% of the people in the US were Republicans, and, 49% were Democrats, and 3% were something else. But let's say we were just talking about, everybody was either Democrat or Republican, and let's say it was 51-49, right? So now the claim is that if you were to reach into the population and pick up, sort of pick out a random person, and if they were, let's say you call them up and they didn't hang up, and as soon as you call them up, and they actually talked to you and said who they were, and okay, then what you would hear would be like the toss of a coin of bias 51%. And every time you reach into this population and pick out a person at random, and you ask them what their choice is, it's as though you're flipping this coin again. So you get to flip this bias coin over and over again, based on the fact that you can pick out random people from the population. Is this clear? Is the correspondence clear? So now, the question of predicting the election boils down to this. You're given the bias coin. You're allowed to flip it. You're allowed to flip it many times. It costs you, but you're allowed to do it. And now you want to figure out what the bias of the coin is. Right? So really the question boils down to how effectively can you do this? How many samples do you need? How close do you get? How confident are you about your answer? Right? So remember that they are really, okay, so there's the true bias of the coin, which might be 51%. Right? Now you flip that coin many, many times. You come up with a sample. Based on that, you come up with a prediction. Maybe you say it's 52%. Okay? Now there are two kinds of issues you're concerned with. One is how close did you get? So that's 1%. And then the second thing is how confident are you about your answer? Right? Meaning, so when Nate Silver did his prediction, he said, well, I think I'm close enough to tell who is going to win, but with 90% confidence. Right? So, okay, so there are two parameters here. How close did you get? How confident are you of your answer? Where does the confidence come from? Well, it comes from the fact that if you flip a bias coin, even though it's biased towards heads, 52%, it could be that you toss it 100 times and it came up tails 51 times. That's possible. Right? The chance may not be high, but it's possible. Maybe there's a 5% chance of that. So you cannot be more than 95% confident about your result, because you know that 5% of the time, if you're only flipping the coin 100 times, it'll actually give you the wrong answer. It'll come up, in terms of what actually comes up, it won't be according to the bias of the coin. It'll be, you got a special sample. So you cannot eliminate that. So you have some chance of error just from that, and that's your confidence. And then there's a question, did you pick a large enough sample that you're close to what the correct answer is? Maybe the correct answer is 51, and you try to get as close as possible. You want to pin it down, and you want to say 51.0001. Well, that's going to cost you. You're going to have to flip the coin lots and lots of times, depending upon how close you want in terms of epsilon. Right? So these are both sources of error. And what we want to do is we want to understand, given a coin of unknown bias which you're allowed to flip, how do you figure out what the bias is? You want a numerical value for the bias, which is close, which is within epsilon, with confidence 1 minus delta. Right? With probability 1 minus delta, you want that your estimate is within epsilon of the correct answer. So now you want to know, given epsilon and delta, which is what you can live with, which is the kind of tolerances you can live with, how many times, what's the number n times that you have to flip the coin? Okay, so that's the central problem in predicting elections. Oh, sorry, okay, well, Dilbert. Well, Dilbert always has something interesting to say, so. Okay, in this case, about picking the right sample size. So it depends upon what kind of epsilon you want and what kind of delta. But if you're this guy, you want to choose your sample size appropriately. Okay. All right. So okay. So let me just say what this problem is again. So you're given a bias coin, given a coin of unknown bias, meaning the probability of heads equal to p. You want to figure out what p is. So want to estimate p to within epsilon. Right? What do I mean by this? What I mean is that your estimate, which we'll call p hat, we want p hat minus p to be less than or equal to epsilon in absolute value. But we cannot guarantee this. Nothing about coins is ever guaranteed, because no matter what, there's some chance that the coin will come up all tails. Right? You toss it 100 times, you could be the unluckiest person in the world, and it could always come up tails. Right? So you can't eliminate that chance. So you want this with confidence 1 minus delta. Okay? So meaning what you want to guarantee is that the probability that p hat minus p is less than or equal to epsilon is at least 1 minus delta. Okay? Or alternatively, equivalently, you want to say the probability that your estimate is more than epsilon away from the true answer is at most delta. Okay. Now, how do you plan to come up with an estimate? Well, there's a very easy way of doing it. The obvious way of doing it is you're going to take this coin, you're going to flip it n times, and you're going to look at the average number of heads. Right? So, So what we'll do to come up with the estimate is flip coin n times, and let p hat be x1 plus x2 plus xn divided by n. Right? The number of heads divided by n. Okay? So our question is, given epsilon and delta, what n should you choose? So given epsilon delta, what n should we choose? Okay, so that's what we are going to try to figure out. And to do this, we're going to try to understand what the probability distribution looks like. We'll try to understand certain properties, and we'll show that these properties, in fact, you can use these to analyze any probability distribution, not just this kind of question, but any question about probability. You can use these tools that we'll actually talk about. Okay, so by the way, if you want to look at the probability distribution when you toss a coin many, many times, well, this is called the binomial distribution. Remember what the distribution of a random variable is? So here we are looking at the number of heads when we toss a coin 100 times. Okay, it happened to be a fair coin, so the probability of heads was a half. So the probability distribution says for every possible value of the random variable, which is number of heads, what's its probability? And so this is plotting it out. Look at the scale here. It's only going from 30 to 70, right? Because if you go from 70 to 100, it's already essentially zero. I mean, it's of course non-zero, but it's so small that we can't even draw it. And similarly, if you want to go left of 30, it's already too close to zero for us to even talk about it. Right? So the number of heads in 100 tosses is very sharply peaked about 50. Okay? But still, it's not exactly 50. There is variance. I mean, there's a pretty good chance you're going to be 5 or 10 to the right, 5 or 10 to the left. How do we know, how does this 5 or 10 scale with the 100, right? How quickly do we get close to 50, right? That 50%, or to, if the probability of heads was p, how quickly do we get to fraction p here? Right? Okay, so this is what we want to study. So, I don't know. How do you guys do on suspense? Do you like suspense or do you not like suspense? Do you like it? Really, I can't stand suspense. It drives me nuts. So I usually like seeing the answer right away and then sort of figuring out how we got there. So let me try the experiment. Let me just tell you the answer right away, and then we'll gradually make our way to it by saying how do we actually, we are going to try to understand how to get there. Okay? So at least you know what we are working towards. Okay, so here's what we are doing. So you flip a coin n times. Right? And probability of heads equal to p. So the expected number of heads, what's the expected number of heads? So let's say x is a random variable, which is the number of heads. So it's n times p. How did you get n times p so quickly? I'm sorry? Oh, you memorized it, okay. But is there a different thing you could have memorized instead? Oh, linearity of expectations, right? So you could have said, well, if you have a random variable for each coin flip, which is 1 if it's a heads, 0 if it's a tails, then the expected value of that random variable is p, clearly. And then by linearity of expectations, if you have n such coin flips, you get n times p. Okay. Now, okay, so this is it goes between 0 and n. There's p, there's n times p. Now what we want to know is, what's the probability we deviate from n times p? Right? That's what we are trying to figure out, because we are going to toss the coin n times, and then we're going to divide by n, and that's going to be our estimate. Right? So we'll come up with some estimate p hat, because what we'll actually do is we'll actually toss the coins, and we come up with some number of coin tosses, which are heads, and we divide that by n. Right? So if this is the actual number of coin tosses, let me call that n times p hat, right? The number is n times our estimate, because we got the estimate by dividing this number by n. And what we want to know is, what's this distance? Right? You know, how big is this distance? And when we divide this by n, we'll get epsilon. So this distance is n times epsilon. Right? This is how far we are from the actual, our estimate. Okay, sorry. Maybe this is only confusing you, so let me actually rename all this. So say we flip the coin n times, and we got some number of heads. So what should we call that number of heads? Should we call it m? So when we flip the coin n times, and we got m heads. So now p hat is m divided by n. Yes? And then epsilon, our error, is p hat minus p, roughly, right? Which is roughly m over n minus p, right? Okay. So what we want to do is we want to understand, which is m minus n times p divided by n. So we want to understand how small this distance is. How small can we expect this distance to be? And the answer is this. The answer is that what we expect this distance to be is roughly square root n. Okay? So we expect the deviation from the mean to be roughly square root of n, or square root of n over 2. Okay? So we'll see how to figure this out, but this is how it sort of goes. Okay? And if you want to know, what we'll actually show by the end of the lecture is that the probability that the deviation is greater than k times square root n over 2 is at most 1 over k squared. Okay? All right, so meaning what? Square root n is small compared to n. So it's telling us that, well, if p was half, then you're pretty close to n over 2. How far could you be from n over 2? Well, if things were really bad, you could be n over 2 far. But it's telling us, no, that's not what you should expect. You should expect to be within square root n of the correct number. Yes? What's k? K is any number. For any k, this is true. Okay? Yes? How did I get it? By looking ahead. Okay, so this is, I told you I can't stand suspense. So, I just told you where we are heading towards. And how we get there, that's, okay, there's still some suspense there. That's life. But what you going to do? Yes? Yeah. See, where did I get the square root of number 2? Yeah, okay, so maybe this was a bad idea. Okay. So, all right, so if you can't stand it, just erase this from your mind, and we'll just get there, and you'll see the result at the end. Yes.
Is the square root of n over 2, is it the distance between np and np hat, or is it epsilon?
No, it's between np and np hat, or np and m.
So that's right, n over 2, right?
Yeah, this is what's of the order of square root n. Okay, so now I claim that from this, we can already figure out, given epsilon and delta, how many samples we need. Yeah, is everybody sort of, can you believe that given this formula we can figure out, given an epsilon and a delta, how many samples we need? Do you want to see it done? Yes? Okay. Okay, so let's figure this out. Okay, so here's our picture. Here's n times p. Okay. We know that if we want, that if we want our estimate to be within n times p plus k times square root n, or n times p minus k times square root n, if we want it to be within this interval, right? The probability that the number of heads does not lie in this interval. So the probability that we fall outside this interval is at most 1 over k squared. Yeah? Now we want to figure out what k should we choose. Well, it's clear, right? Remember we had an epsilon and a delta. So what was delta? It was the chance of failure. So we let delta equal to 1 over k squared. Right? That's our chance of failure. We want to make sure that if the number of heads falls inside this interval, then we are within epsilon of the correct answer. So we want to make sure that that if we choose p hat to be, so how do I want to say it? So I want to say k times square root n divided by n, right? We want this to be equal to epsilon. Does everyone see this? Okay, so let's see. What's p hat? P hat was the number of heads divided by n. So what's the range that it lies in? Well, it's at most n times p plus k times square root n divided by n, and it's at least n times p minus k times square root n divided by n. This was p plus k divided by square root n. This is p minus k over square root n. Actually, remember we had a square root n over 2. Let's just put that in because we want to be accurate. So it was k times square root n over 2, square root n over 2, over 2, so over 2. Yes? Okay. So what do we have? We have epsilon equal to k divided by twice square root n, which means that n equal to k squared over 4 epsilon squared. Yes? Sorry, give me half a second. Yeah? K squared is delta, so you get 1 over 4 epsilon squared delta. So that's the number of coin flips you need to use. So if you tell me an epsilon and a delta, and you say, I want to be within epsilon with confidence 1 minus delta, how many times should I flip the coin? This is the number of times you must flip the coin. 1 over 4 epsilon squared delta. This is sufficient. Right? This may not be the best estimate, but this is the one that we'll calculate. This is the one we'll prove. Okay? Then if you want to get fancy, you can prove better bounds than this. I'll even tell you a better bound that we can prove. But this is the one that we can do sort of in this class. Sorry, you had a question? May I correct that for a moment? It was not epsilon there. It's a matter of normalization. We are saying the chance that the number of heads that you get deviates from its mean, which is n times p, right? By more than square root n over 2, by more than k times square root n over 2, is 1 over k squared at most. Yes? Okay.
And then we started here.
Yeah.
And
then something happened. Okay. All right. So let's talk about that for a moment. So what we did here was we are just doing a translation between number of heads that we see versus epsilon. Remember, to get the estimate, we took the number of heads and we divided by n. Right? So if the number of heads deviated from the expected number by some number like k times square root n over 2, that's a number, that's a large number, right? It might be 20.
so we just had to take that as our,
Right.
want this to be our value.
Yeah, so k is something we'll figure out later, but we want to be within this much of the expected number of heads. And then we said, how big should this number be so that we are within epsilon of the correct answer? Once we divide by n, right? Because we want the estimate to be within epsilon. The estimate is the number of heads divided by n, right? So we take our estimate p hat is the number of heads divided by n, which is what? Well, which is at most n times p plus this number divided by n. Well, p we want, np divided by n we want. That's the actual answer. So how much did we overestimate by? It's this number divided by n, which is k over 2 square root n. So this is epsilon. Okay? So we said epsilon is that number, which is k over 2 square root n.
So we started out saying k square root n over 2 is our arbitrary boundary that we want. And we want to figure out.
Now, what's the value of k such that k times square root n over 2 divided by n is epsilon? Okay? Okay, now we also said that we are within these limits with probability 1 minus delta. Well, no, we are within these limits with probability, except with probability 1 over k squared. So 1 over k squared is delta. That's the chance that we get an error, that we make an error, right? That we are not within epsilon. And so that's delta. So delta is 1 over k squared. And then substituting, we get n is 1 over 4 epsilon squared delta. Yes. How did I get? Oh, how did I get that? Oh, I pulled that out of my hat. So that's something we'll prove. Okay, so what we're going to show later is that if you toss a coin n times, right, the chance that the number of heads is different from the expected value by more than k times square root n over 2, that chance is at most 1 over k squared. Okay? Okay. So remember this number 1 over 4 epsilon squared delta. Oops. So if you want epsilon and delta, then the number of times you must flip the coin is, then n should be equal to 1 over 4 epsilon squared delta. So for example, if you wanted epsilon equal to 0.1, delta equal to 0.05, then this number becomes 1 divided by 4 times 0.01 times 0.05, which is what? It's 100 times 20 over 4, which is 500. So it says, so this is going to be a very crude estimate, but even this crude estimate is sort of interesting because it says it doesn't matter how big a country you live in. It can be 100 million people, it can be 1 billion people, it doesn't matter, right? If you want to be within 0.1, if you want an estimate which is within 0.1, which is not that good, it's 10%, right? If you want an estimate within 10% of the correct answer, with confidence 95%, then all you need to do is pick 500 people at random. That's all you need to do. Right? Okay, so this is sort of the remarkable phenomenon which is behind polling. That the size of the population does not matter. All that matters is that you reach in and grab a random person to ask each time. Right? That's not easy to do. Okay, that's a difficult question. And this is where statisticians spend a lot of their time trying to figure out how do you grab this random person? How do you make sure there are not biases? And how do you do it in a manner which is not too expensive? Okay? But this is the basic theory. Now there are two parts to this answer. One is the dependence on epsilon. This is called the accuracy parameter. It's how accurate your estimate is. And then there's delta, which is the confidence in your answer. Right? What's the chance that your answer is incorrect, that it falls outside the range? It turns out that even though the constant here is wrong, the 4 you can improve upon. The epsilon squared you cannot improve upon in general. It's really there. But the dependence on confidence that we got here, which is 1 over delta, is actually, you can do much, much better than this. So there's something called, which we call the Chernoff bound, which we will not talk about here, right? I won't derive this, but I'll just mention it to you for those who are interested. So what it shows is that you can get away with n equal to big O of log 1 over delta divided by epsilon squared. So instead of having a 1 over delta, you can replace it by log 1 over delta. Okay? The other way to think about the Chernoff bound is that what it says is the probability. How did I say it before? Okay. So the probability that the deviation is greater than k times square root n is at most e to the minus some constant times k squared. So instead of being 1 over k squared, it becomes exponentially small. Okay. Well, maybe you don't want to see e here. So let's make it 2 to the power of minus some constant time. Okay? Okay, so, these are all things that are true, but these are not things that we'll prove here. Okay? So it's for you to know that the way this binomial distribution behaves, there's this width of square root n, and then as you keep marching out, multiples of square root n, the probability falls off exponentially. So the tail of the distribution falls off very, very quickly. Okay? Yeah. So there was a question? Yeah. No, I haven't. So we'll get there in a few minutes. Okay. So should we take a very brief break, and then we'll get down to proving things. Okay. Okay, so to do everything that I told you about so far, what we need is some measure of the spread of a distribution. Okay, so here's the notion. You know, here's our picture. Here's our probability distribution. It looks something like that, right? So that's the expected value of x. That one, right? So this is right. So we are plotting A versus probability x equal to A, right? That's the probability distribution. That's the expected value. And now we want to understand how spread out this probability distribution is. So for example, we might have two different probability distributions. This one, that one, they both have the same expected value, right? That's the expected value of x. Is equal to expected value of y, which is this blue random variable. But we think of y as being less spread out than x, right? So if you want to know what's the probability that you're going to be within this much of the expected value, in the case of y, it's very, very high. In the case of x, well, there's a lot of probability that it's outside, right? So if you wanted to know what's the chance that you are within this interval, where in the case of y, the chance that you're not in this interval is sort of, it's that area. Right? In the case of x, it's that area. Oops, sorry. It's that area. Right? Okay, so what we want is some way of estimating this quantity. And for every, you know, we don't know in advance which limits we want. We want one number, like the expectation, that gives us a measure of how spread out the distribution is. And that one number is called the variance of that random variable. Okay, so the variance of x is just, so let's say the expected value of x is mu. So mu might be a number like, let's say think of mu as, in this case, let's say the expected value of x was 50. So this is 50. So the variance of x is just the expected value of x minus 50 whole thing squared. Okay? What do I mean by this? So let's write this out. This is the sum over all A of the probability x equal to A times x minus 50 whole thing squared. Right? It's the expected value of the quantity, x minus mu whole squared. Does that make sense? So in other words, what we are counting is, for every value A, we are saying, what's the probability x takes on this value, and then how far away is it from the mean? Okay. Now, why did we square x minus mu? Can anyone say? Well, what if instead of squaring it, we just left it the way it was? What if we took x minus 50? Yeah. Yeah, it would end up being 0, right? Because the distribution goes to the left, it goes to the right, a part of it would be negative, part positive, and it would all cancel out. And so that's why we take the square, right? To try to get a positive value, no matter whether you deviate to the right or to the left. So the more probability you put out here, the higher the variance goes. If you push some of as the random variable gets pushed farther and farther out, x minus a whole squared grows quite quickly. And so this quantity really reflects how spread out the probability distribution is. Yeah?
What is the advantage of squaring over, say, taking the absolute value?
Yeah, the advantage of squaring over, you're absolutely right. So what you really want to do is take the absolute value of x minus mu. The problem is the absolute value is not a well-behaved function. It's discontinuous. And so nice things don't happen with absolute value. So as you'll see, variance is nice. All kinds of nice things happen. Because computing these quantities is a real pain. But with variance, we have these nice properties which make it very easy to compute variances. And that's why we take the square. Okay. Now, one thing you should observe is that we are taking the expectation of a squared quantity. Okay, so if we want to be, meaning that the units, for example, if this is length, the units of variance would be length squared. It's the wrong unit. So if you want the correct unit, we have to take square roots. And so if we take the square root of the variance, that's really the quantity we are interested in. That's called the standard deviation, and it's usually denoted by sigma. That's it right there. Okay? So these are the two quantities which for us are measures of how spread out the probability distribution is. The variance and the standard deviation, right? Which is the expected value of the square of the deviation versus the square root of that variance, right? Depending upon which units you want to work in. Okay. So let's do an example. So let's say we have a bias coin. So probability of heads equal to P. Probability of tails is Q, is 1 minus P. Okay. So now, what's the expected value? So let's say x equal to 1 if heads, 0 if tails. Then the expected value of x, which we are calling mu, is P. And now what's the variance? So variance of x was what? It's expected value of x minus P whole squared, right? So it's with probability P, the value is 1. So the square of the deviation from P is 1 minus P whole squared, plus with probability Q, it's 0. And so the deviation is P minus 0 whole squared, right? So times P whole squared. 1 minus P is Q, right? So you get P times Q. This is P, Q squared, so you get Q plus P, which is, this is 1, so you get P times Q. Right? P times 1 minus P. So sorry, I don't know why I introduced Q in there, but it's how you want to remember it. If you want to think about P and Q, it's P times Q. If you just want to think in terms of probability of heads, it's P times 1 minus P. Yes. The variance of x. So what's x? X is this random variable which is 0 with probability P, 1 with probability 1 minus P. Okay, so now to compute its variance, you take the expected value of x minus the mean of x whole squared. What's the mean of x? What's the expected value of x? It's P. So you want the expected value of x minus P whole squared. Right? So how do you do that? With probability P, x is 1. So what's x minus P whole squared? It's 1 minus P whole squared with probability P. So you get P times 1 minus P whole squared. With probability 1 minus P, the value is 0. X is 0. So the deviation from the mean is P. So you get P squared times the probability. The probability is 1 minus P. Right? Q is 1 minus P. So you get that, and now you simplify. Okay? Now, it turns out that there's a very useful formula that you can use. So you don't have to really play with this quite as much. It's usually useful to use that formula. So what it says is that the variance of x is the expected value of x squared minus the expected value of x whole thing squared. Right? If you call the expected value of x mu, then it's the expected value of x squared minus mu squared. How do you see this? It's sort of easy, right? What you do is variance of x is the expected value of x minus mu whole thing squared, which is what? It's the expected value of x squared minus 2x mu plus mu squared, which is what? Linearity of expectations, it's expected value of x squared minus or plus expected value of minus 2 mu x plus expected value of mu squared. What's the expected value of mu squared? It's mu squared. Mu squared is just a number. It's a constant, right? So this is just mu squared. What's the expected value of minus 2 mu x? Minus 2 mu expectation of x. Right? If 2 mu was 5, if 2 mu was 5, then this is like minus 5 times x. What's the expectation of minus 5 times x? It's minus 5 times the expected value of x. And then expected value of x squared. But expected value of mu, this is equal, expected value of x is just mu. So this is minus 2 mu squared plus mu squared. So you just get expected value of x squared minus mu squared. Okay, so why is this useful? So for example, with this bias coin, probability of heads equal to p. What's the expected value of x squared? So x is 1 with probability p, 0 with probability x equal to 1 with probability p, 0 with probability 1 minus p. What about x squared? It's the same, 1 with probability p, 0 with probability 1 minus p, right? Everyone see that? Because if x is 1, x squared is 1. If x is 0, x squared is 0. So expected value of x squared is just p. So you get, and what's the expected value of x? It's also p. So variance of x is expected value of x squared minus expected value of x whole thing squared, which is p minus p squared, which is p times 1 minus p. Same thing as we got before. Right? So it's just, sometimes it can be easier to do this. Okay. Now, let's move on with things. Now suppose instead we had a bias coin and we flipped it n times. Okay, so we flip our bias coin n times. So we have x equal to x1 plus x2 plus so on plus xn. Okay? We want to know what's the variance of x. Okay? What we'd really like is the linearity of variance. Okay, wouldn't that be nice? If we could just write that this is variance of x1 plus variance of x2 plus variance of xm. Wouldn't this be great? Because then we could just say this is n times p times q. Right? N times p times 1 minus p. Okay? It turns out this is true. Okay? But for this to be true, these random variables have to be independent. It's true if the xi's are independent. Okay, so make sure you remember that it's not true in general. Okay? for example, the variance of x squared is not the same as is not, oh, sorry, what am I saying? Okay, the variance of 2x is not the same as 2 times the variance of x. Okay, the variance of x plus x, the variance of x1 plus x1 is not 2 times the variance of x1, right? Because you have to check that the variance of 2 times x is 4 times the variance of x, because we are squaring, right? But if they're independent, then the variances add up. And this is sort of a very interesting phenomenon. Okay? So what this tells us is that the variance grows linearly. But remember, we said that the variance is the wrong units. It's like length squared. If we really want the same units, we have to take the square root. Okay? So what we really want is the standard deviation. Sigma of x, which is the square root of the variance of x. And that's equal to square root of n times p times 1 minus p. Okay? But now, remember, p and 1 minus p are unknown. These are the bias of an unknown coin, right? It's an unknown bias. So how do we figure out p times 1 minus p? Well, we know it's less than 1. So we may as well say the standard deviation is less than square root n. We can even say the maximum value of p times 1 minus p can take on is when what? When p is what? It's half, right? And then you get n times half times half. So when you take the square root, you get n times a half. So this is less than or equal to square root n divided by 2. Okay, so that's one mystery solved. That's how I got the square root n over 2. Okay? Okay. So now, are you ready for the next one? Should we solve the next mystery? And then hopefully maybe there's time to do a little more, maybe not. Okay. So how's your stamina? Should we take a 1-minute break? No? Should we charge ahead? Yeah, okay. Okay, so now, here's a fact about random variables. Okay? It's called Chebyshev inequality. Okay, so what it says is, suppose you have a random variable x such that the expected value of x is mu. Okay? And the standard deviation is sigma. Okay, one way I can write that down is by saying, oops. Oh, what happened there? Okay, well, so let's say that the variance of x is sigma squared. Sorry, can you even see this? Okay, so say that the variance of x is sigma squared. Yeah, so the standard deviation is sigma. Then what Chebyshev's inequality says is that the probability x minus mu is greater than or equal to k times sigma is at most x minus mu is less than or equal to 1 over k squared. Yeah?
For any random variable?
For any random variable. Okay? Yeah, because you see, it's very hard to prove things for something particular, right? The reason you can prove this, why it's so simple, and we'll prove it, and you'll see why it's true, is because it's completely general. Okay? Now, okay, so now given this, everything I said in the beginning sort of holds up. These are the two things that I was counting on. The fact that the variance when you flip a coin n times grows linearly in n. So the standard deviation grows as square root of n. Okay? That's why things sort of bunch up. And then Chebyshev's inequality, right? Which says the chance that you deviate goes down quadratically in terms of the number of standard deviations. Okay? All right, so to prove this bound, we need one more bound, which is called Markov's inequality. Okay, Markov's inequality says this. So suppose a random variable x is always non-negative. So you have a non-negative random variable. So it always takes on values which are 0 or greater. And the expected value of x is mu. So then it says the probability x is greater than or equal to k times mu is at most 1 over k. Okay? Now, this inequality is very simple to prove. You could think of it as a seesaw inequality. Right? Is that what it's called? This children's swing, right? A seesaw, right? So imagine that you have a seesaw. Okay. Here's its center of gravity. Here's where it sits. What sits on top of this seesaw is your probability distribution. Right? Now, if your probability distribution is sitting on top of the seesaw, and this is the expected value, then everything should balance out. Well, sorry. What am I saying? Okay, so, sorry. So, all right, sorry. So let's say that this is your expected value, and this is where your seesaw is. Now, So remember that the expected value is the balance point of the probability distribution, right? So everything balances here. But now this is 0, right? You have a non-negative random variable. This is mu. And you want to know how much of the mass sits to the right of mu, of k times mu. Right? So I claim that if you want to maximize this mass, if you want to maximize the mass that you put on this side, if you ever sat on a seesaw, well, you want to shift in as close to the balance point as possible. So you maximize the, if you have a small person, you can move them out far and they'll balance everything out. So if you want to maximize the weight here, you want to push it as close to the balance point as possible. Whereas anything on this side, if you're trying to maximize that weight, you want to push this as far left as possible. Right? Meaning that the only two places where the probability distribution should be supported, if you want to maximize the mass to the right of k times mu, is to support it at this point and at that point, and nowhere else. Okay? But now, how should you distribute the probability distribution? I claim that you must have k minus 1 over k of the probability distribution on this side and 1 over k on that side, and it'll exactly balance out. So that's the maximum amount you can put to the right of k times mu. Right? And that's what Markov's inequality says. Okay, so once we've proved this, we can go back and prove Chebyshev's inequality. So the way you prove Chebyshev's inequality is you define a new random variable. So we want to prove that if x is any random variable, its expected value is mu, variance is sigma squared, probability x minus mu, absolute value, greater than k times sigma is at most 1 over k squared. So to prove it, you just define y equal to x minus mu whole squared. Okay, so y is a random variable which is non-negative. Why? Because it's a square. It's already squared, so it can never take on a negative value. Expected value of y is what? It's sigma squared, right? Because expected value of y is expected value of x minus mu whole squared, which is the same thing as the variance of x, which is sigma squared. So what this is saying is you have a non-negative random variable y, apply Markov's inequality. So by Markov, we are saying the probability y is greater than or equal to k squared sigma squared is at most 1 over k squared. Right? That's Markov's inequality. The chance that your k squared times the mean is at most 1 over k squared. And now just write out what this means. So this is the probability that x minus mu whole squared is greater than or equal to k squared sigma squared is at most 1 over k squared. X minus mu whole squared is greater than or equal to k squared sigma squared if and only if x minus mu absolute value is greater than or equal to k times sigma. And that was Chebyshev's inequality. Right? So it's almost barehanded, right? It's just, all it talks about is sort of a children's swing and change of variables. And that's all it takes to prove Chebyshev's inequality. Yeah? Yes?
Why did we have to assume that x was greater than 0?
Why did we have to assume that x was non-negative? So let's see this. So we are saying, okay, so let me see. So we are saying, suppose that you knew that there's a probability distribution. This is the expected value of x. We want to say that the chance that you are, this is 0, the chance that you are more than k times the expected value of x, we want to show that the chance of being here is small, right? But if x can take on negative values, it could be that with probability half you're out here, right? With probability half you're out here, and with probability half you're equally negative. And you can make these 2 points as far apart as possible, as you want, while keeping the expected value here. Right? Your probability distribution in general doesn't have to look like that, right? It could also look like two bumps like this, or it could look like that, right? There's nothing that says probability distributions have to look like that nice bell-shaped curve. And so if all you know is that the expected value is here, you know that there's a lot of stuff on that side, there's as much stuff on that side as there's on that side, it all balances out. But you can balance things out by pushing things, far on both sides. But saying that x is non-negative says that you can't push things out too much on this side, right? And now you're asking, can you push things out a lot on that side? And that's this balance beam question. So if you have a fat person sitting on this side and a thin person sitting on that side, what can the difference of weights be in order to still make it all balance out? And the answer is, this person has to be at least 1 over k of the weight of that person for it all to balance. If this person is any lighter, it's not going to work. Right? So that's, yeah.
So as long as x is on a finite interval, it will still probably work too, right?
Right, yeah, the fact that it's 0 is something that's convenient for us.